All right, today we're diving into something that is, no joke, a revolutionary upgrade to how Bitcoin works. We're talking about signatures, but in a way that feels almost like a magic trick. We're going to uncover how you can make a whole bunch of signatures look like just one. Let's get into it.
So here's the central question, and it really does sound impossible, right? Imagine 100 people, or even 1,000, all need to co-sign a Bitcoin transaction. But when you look at it on the blockchain, it just looks like a totally normal, everyday transaction signed by a single person. How is that possible? Well, that's the puzzle we're going to solve today, and the answer has huge implications for both privacy and efficiency on the network.
Okay, so before we can get to the whole invisible part of this, we've got to understand the foundation that makes it all possible. And that foundation is a special type of digital signature that came to Bitcoin with the Taproot upgrade. It's called a Schnorr signature, and trust me, it's the key that unlocks everything we're about to talk about. So what exactly is a Schnorr signature? Well, you can think of it as a sleek, modern upgrade to the older signature type Bitcoin used for over a decade. It's designed from the ground up to be super simple, really efficient, and mathematically just clean. And it's that clean mathematical structure that gives it some truly amazing properties.
The first thing you'll notice is its size. A standard Schnorr signature is just 64 bytes long. That's it. It's made of two 32-byte numbers, making it incredibly compact. Now, this is a fantastic improvement for saving space on the blockchain, which, translates directly to lower fees for you. But the real magic isn't just that it's small. This right here is the superpower, linearity. It's a fancy word for a really simple idea. You can take multiple Schnorr signatures, or their public keys, and literally just add them together to create a brand new, perfectly valid signature or key. This simple act of addition is the secret sauce that makes the whole invisible multisig concept work.
All right, let's get to the main event. Now that we know about this linearity superpower, we can see how cryptographers came up with the dream scenario for multisig transactions. Multisig is just short for multisignature, where you need several people to sign off on a payment. The dream was to combine all their keys and all their signatures into one single package that looks exactly like a normal one-person transaction.
The goal itself is actually pretty simple to grasp. Let's say Alice has a public key, and Bob has a public key. With Schnorr, they can just add them together to create a totally new, shared, aggregated public key. And the coolest part? This new key looks and acts just like any other public key on the network. There's no way for an outsider to tell that it was secretly created by 2 or 3 or 100 people.
And at first glance, the process for doing this seems beautifully simple. First, all the participants combine these one-time use secret numbers called nonces. Then, they all agree on the transaction they're signing. After that, each person creates just a piece of the final signature. And just like they did with the keys, they simply add all those pieces together. The result? A single 64-byte signature for their single aggregated key. It's so elegant. But I have to give you a massive warning, straight from the source material. This naive protocol is dangerously, fatally flawed.
Yeah, that simple, elegant design we just looked at, it's hiding a critical, show-stopping problem. We're talking about a vulnerability so bad that if someone uses it, they can steal all the money from the group without needing anyone else's signature.
This is what makes cryptography so incredibly tricky. An idea can look perfect, it can look elegant, but it can have a fatal flaw hiding right there in plain sight. And this one's a doozy. It's called the key cancellation attack, and it cleverly uses that simple addition property, the one we thought was a superpower, against the group. A malicious person can wait for everyone else to show their public keys, and then they can specially craft their own key to mathematically erase someone else's from the final equation. Let me show you exactly how this works.
Okay, so let's start with our honest participant, Alice. She follows the rules, she generates her key, and she shares it with the group because she wants to create a shared 2 of 2 multisig wallet with Bob. So far, so good.
Now here comes the attack. Our malicious Bob sees Alice's key. But instead of just creating his own normal, independent key, he does something sneaky. He takes the key he secretly wants to use for himself, and then he mathematically subtracts Alice's public key from it.
And this is the brilliant, devastating result. When the protocol goes to add their keys together, Alice's key plus Bob's tricky key, the math just works out. The positive YG from Alice and the negative YG from Bob's key, they cancel each other out completely. The final aggregated key is just Bob's key. Alice has been completely erased from the equation, and Bob now has sole, total control over all the funds.
So that's terrifying, right? It seems like this whole amazing idea of an invisible signature is completely broken. But don't worry, the story doesn't end there. Cryptographers are a clever bunch, and they've developed solutions to defeat this exact attack, which is what led to the secure protocols that we actually use today.
The fundamental fix is all about breaking the attacker's advantage, which is timing. You have to force everyone to commit to their public key before they get to see anyone else's. A simple way to do this is to have everyone first share a hash of their key, like a digital fingerprint. Once everyone's hashes are on the table, then they can reveal their actual keys. This way, Bob can't tailor his key to cancel Alice's, because his has been locked in from the start. But as the source material points out, while that basic fix sounds simple, actually implementing it securely involves a lot of trade-offs. There isn't just one single perfect protocol for every situation. You end up having to balance things like communication speed, overall complexity, and different security guarantees. And this has led to a whole family of related protocols.
This is where things get really practical. With the MUSIG family of protocols, you can see the trade-offs right here. MUSIG 1 was kind of the first big attempt. It's pretty straightforward, but it requires 3 back-and-forth rounds of communication. Then came MUSIG 2, which is a huge improvement. It only needs 2 rounds, and you can even do one of those in advance, making it way faster. And then you have even more advanced versions, like MUSIG DN, which solve for more obscure and complex attack scenarios.
So, with all these different options, you're probably wondering, okay, which one do people actually use? Well, thankfully, the industry is pretty much settled on a practical standard that gives the best all-around balance for most things you'd want to build. And that standard is MUSIG 2. It really hits the sweet spot between being super secure and really efficient. It's fast, it's been heavily studied, and it's been formally standardized for the whole Bitcoin community as BIP 327. So for developers building wallets and other services today, MUSIG 2 is the gold standard, the go-to choice for creating these invisible multi-signatures.
So, let's wrap this all up. What does all this complicated cryptography actually mean for you, the person using Bitcoin? Well, a few really important things. First, lower transaction fees. A single tiny signature is always going to be cheaper than paying for 3 or 5 or 10 separate ones. Second, and this is huge, you get much better privacy. Nobody can look at the blockchain and tell if your funds are controlled by one person or a whole committee. And finally, this tech is a crucial building block for the future. It helps things like the Lightning Network become way more efficient and scalable.
And that really brings us to the final exciting thought here. We've gone from these simple individual signatures to these smart, combinable ones that are smaller, more private, and way more powerful. This isn't just a small step up. It's a fundamental change in the tools that developers have to work with. So the real question to leave you with is, what comes next? What kind of new, crazy, innovative applications are people going to build on top of this powerful new capability?